This is a photograph of a standard two-lane highway in Uganda. On a bus journey here, the vehicle's motion is constantly changing. The driver pushes to high speeds on the open stretches, slows down to crawl over speed bumps, and completely stops to pick up passengers. If we tried to record every moment of acceleration, deceleration, and waiting in a logbook, we would quickly fill pages with text. Analyzing that trip to find exactly when the bus was moving fastest would be difficult and slow. This line graph is the mathematical solution. Translating the journey onto a grid compresses a complex trip into a single visual story. We immediately spot the stops, speeding, and slow traffic. Mastering these patterns allows you to recognize the mathematical logic built into every trip. We tabulate Kampala at 0 kilometers, Jinja at 84, and Igonga at 123. We plot using even scales like 10 or 20. On a distance time graph, an upward line means moving away, a flat line means stopped, and a steeper slope indicates higher speed. A correctly plotted distance time graph serves as a precise historical map. It proves exactly where an object was and how fast it was moving at any specific second in time. Let's test this with a real scenario. A taxi leaves Masaka at 7 a.m., arriving in Lukaya 30 kilometers away at 7:30. It stops to load passengers for 15 minutes, then drives the remaining 100 kilometers to Kampala, arriving at 9:15 a.m. Which leg of the journey was the taxi driving the fastest? We start by organizing the data. We chart the initial drive to Lukaya at 7:30. Crucially, we must log a second entry for the 15-minute stop. At 7:45 a.m., the taxi is still precisely 30 kilometers from the start. We finish the table with the arrival in Kampala. When we plot these points, the physical weight in Lukaya translates into a perfectly flat horizontal line on our grid. The x-axis value locks at 30 kilometers for a quarter of an hour, representing the 15-minute passenger stop. To find the fastest leg, we look at the gradients. The calculation confirms the final leg to Kampala covers 100 kilometers in 90 minutes, moving the taxi at over 66 kilometers per hour. This exceeds the 60 kilometer per hour pace of the first leg. Up to this point, we have only looked at graphs tracking distance. If we change the vertical y-axis to speed, the visual rules of the graph change completely. This side-by-side view shows a common trap in graphing. On the left, a flat line on a distance time graph means the object is stationary, but on the right, a flat line on a speed time graph means the vehicle's speed is holding steady at a specific value. It is not resting, it is moving at a constant speed. On a speed time graph, the object is only stopped if the line drops all the way down to hit 0 on the vertical axis. Reading a shape on a grid without first verifying the units on the y-axis will cause an incorrect interpretation of the event. Always check the labels before you read the lines. Consider a taxi pulling into a crowded park like this one. It is moving at 30 meters per second. The driver sees a pedestrian, brakes, and stops in exactly 3 seconds. How do we figure out the total distance it took to stop? Here is the graph of that deceleration. Because the vertical axis is speed and the horizontal axis is time, we can calculate the distance traveled by finding the geometric area underneath the graphed line. The line and the axes form a triangle. We take the formula for the area of a triangle, 1/2 times base times height. We multiply 1/2 by our 3-second base and multiply that by our 30 meter per second height. The resulting area is 45, meaning the taxi traveled exactly 45 meters before fully stopping. As you analyze these grids, keep in mind that the line you are looking at is not a drawing of the physical road. It is a mathematical relationship between two variables. If a line slopes downward on a graph, it does not mean the vehicle is physically driving down a hill. On a distance graph, it means the vehicle is returning. On a speed graph, it means the vehicle is slowing down. When it comes to flat lines, you can rely on this simple check. For distance, flat means asleep. For speed, flat means cruising steady. This chart summarizes the key differences. By recognizing these distinct shapes and confirming your axes, you can tell if an object is accelerating, resting, or returning. Master these differences, and you master the mathematics of motion.